Let me just continue where we ended yesterday. So, just as a reminder, about the commutation relations in the Cartan basis. Remember, we had a collection of Cartan generators which commute with each other, and the number of them is given by the rank of your Lie algebra. Then we have the commutation relations between this H boldface that represented the collection of all the Cartan generators, written in a condensed form, okay? And this is the commutation relations with your generators associated with your roots alpha vector sign. So remember, E means that you have a generator associated to a given particular root, okay? So when you commute with each one of these generators, you will get for eigenvalues the components of those root vectors, okay? Then we'll look at the commutators of the generators associated with a given root with the commutators associated with the mirror reflected root, okay? This is what I mean by minus alpha. And here we look at the commutation relation between among the other generators associated with the other roots. And this commutation relationship is a little bit more complicated because it depends on these capital N coefficients, which depend on two integers, okay? So I'm going to give you a specific example of what these commutations relations look for the SU3 algebra, okay? So let me just proceed. Well, I gave you, I wrote down the properties of these coefficients. I mean, we'll give you a specific example. Then for the SU2 algebra, we have the ladder operator, which raises, you go up the ladder, and these are the lowering ladder operator. And in this case, your Cartan element, your Cartan generator only corresponds to the set component of the angular momentum. That was for the SU2 case. But let's look at the SU3 case in particular, which is the Lie algebra associated with the strong interaction. And I gave you the representations of the Gelman matrices, okay? So I don't know what happened to that paper that I gave Fang, remember? With the Dynkin diagrams and the Cartan matrices. That paper in any case, essentially today we'll be focusing on, if you look at page 310 through 312, you are going to see a bunch of diagrams. Yes, I left my glasses over there, but I think it's 312 through 312. 310, 311, 312. Okay. It's in your book too, the Dynkin diagrams. Okay. So if you look at the SU3 algebra, the rank of the SU3 algebra is 2. This algebra is associated with the algebra you call A sub 2, the A series. And then it turns out that all the 6 roots of your algebra, remember you have two roots that correspond to the Cartan generators, which are 0. You don't include those root vectors. Then you have 6 of them, which are the other generators. So they all of them have the same length. So many authors like to normalize the length of those vectors by this condition that the rank of your Lie algebra, in this case, the rank of my Lie algebra is 2. Each generator is scaled by a factor of lambda. So you have 6 of them. They all have the same length. So essentially, this normalization factor is the square root of 1/3. It's just a convention that people use. So let's look at for example, at the commutators associated with root number 1 and root number 2. So it's this numerical coefficient. And remember, root vector 1 plus root vector 2, you have 1 plus 2 is 3. It's just a symbolic notation to let you know that when you combine the commutator of E1 with E2, you get E3 because 1 plus 2 is equal to 3. I mean, this is the notation the book uses, but you know what I mean is the vector sum of root number 1 plus the vector sum number 2 gives you the vector sum of root number 3. Okay? It's just a symbolic way of, condensed notation. Okay, so let's proceed to evaluate. Okay, so these structure constants associated with those commutators are given by this formula, where n in this case is 1 and little m in that case is 0. Okay, so as a reminder, n and m, they are the markers. the black and blue markers, please. Yeah, Dugan, please. Thank you. Yeah.
We don't have either of those.
Well, okay. Yes. Thank you so much. So, remember when we said earlier yesterday that when you have your root vectors, not only the simple root vectors. When your root space is comprised of two subsets. One subset is what you call the simple roots, and the other subset are the roots which are obtained by linear combination of your simple roots. Okay? So in general, when you have two roots, if you have a pair of beta and alpha are two roots, then remember what I mentioned yesterday, that you perform the linear combination of the sum of the two roots, and then you add another. You add 2 alpha, etc., until you reach a value of n when you do no longer have a root. This is no longer a root. Okay, so by doing this, you are able to pick out, select the value of n, which is the one value that you plug into this formula. And then doing the same thing with the minus combination, you are able to pick up the value of m. Okay, this is a root, and then so forth. And then you reach a value of m, not necessarily the same thing as n, because here I'm taking the difference. Upstairs I will take in the summation. If it's not a root, then this will allow you to select the value of m. Of course, okay? So the values of n and m depend on which algebra you are talking about, okay? Maybe I should use a different color because you can hardly see, right? Can you see this better, no? Yeah, okay. So for the SU3 algebra, which is a rank 2 algebra, the values of n and m turn out to be n equals to 1 and m equals 0. And why? Remember when we drew the hexagon fan yesterday, when we had, for the case of SU2, we had actually one root alpha and another beta, and then we drew the combination of beta plus alpha, and then you have 1, 2, 3, and then you do the mirror images, okay, and then you get your nice hexagon. Okay, so this is essentially.
That's SU2.
Yeah, for SU3. SU3 has rank 2. Okay, so you have 2 Cartan generators and six roots which are not Cartan. So 6 plus 2, this is related to the SU3 algebra. Okay.
That's the G one.
Yeah, which the rank is 2, so you need to have a 2-dimensional space to represent them. Okay, so in this case, and that's all the roots you will have. So therefore, this is why the value of n equals to 1. N equals to 1, because you don't have here, you do not have the beta plus 2 alpha.
So
actually, it's not beta plus n alpha is not a root. So
Yeah.
beta plus n alpha is a root, but
Yeah.
beta plus n plus 1 alpha isn't a root. So
Yeah.
you take the one before it, right?
Yes. Okay, so in this way we evaluate the n coefficients, and this is what you get. Okay, and then from the symmetry property of the coefficients, we're able to obtain the values of the other combinations. Okay, I gave you the properties of n, and all of this is in your book, by the way, in that chapter of Dynkin diagrams. Everything is spelled out in your book. Okay.
So 1,2 just means first root and second root in the subscript of n.
Yes.
Yeah. So 1,2 just refers to the first simple root and the second simple root. Is that right?
It refers to the. Let's go back to our earlier. To the. Well, they are not necessary. They are not necessarily simple roots. They are just roots. This is the root number 1 and root number 2. Okay, this is the generator associated with root number 1 and associated with root number 2.
Which corresponds to alpha and beta in your
My case, no. Okay. In this case, well, yeah, you can say that those are the first. You can choose the first root to be the first two simple roots, and the remaining ones are not the simple roots. Okay.
Don't you always choose the subscripts
Yeah.
for n to be the simple roots?
No. You choose them to be all the roots, including the simple roots. Okay. Okay.
So similarly, we would have one for the alpha plus beta as well. So
Yeah.
1n1,3 is also a possibility that we need to find.
Yeah, so we'll see. I'm going to spell them out explicitly. So okay, so let's go ahead and write the canonical commutation relations of the SU3 algebra for all the roots. Okay, so here I have because the algebra has rank 2, my eigenvectors have only 2 entries because the algebra is rank 2. So this space here is only 2-dimensional. It's the blackboard, okay? So I have 2 entries. Entry number 1, entry number 2. So this means when I take the commutator of H1 with my generator associated with root number 1, and minus 1 is the mirror root. Okay, the plus 1 is one root, minus 1 is the mirror reflection. Okay, so I will get this plus or minus, depending if I take one root or the other, 1 times my eigenvector, my root. When I take the commutator of H2, which is my second element of my Cartan algebra, with this generator I get 0 times that. And then when I combine the components of H1 and H2, commutators, then I get this vector 1, 0.
So 1, 0, where did you compute that? Did you compute that before?
Yes, I compute that from remember H1 associated with in generator associated with a given root, call it J. Okay, you're going to have my eigenvector and then the component.
2, right, for H2?
Yeah, and then okay, and then I did the same thing with the generator number 2. Okay, this is root, so I have to look at my root vector, but I have to look at the second component because I have here my second generator, and I have my eigenvector. Okay, I'm not using the Einstein convention.
Okay,
Yeah.
so alpha J1
Yeah.
is alpha, so it's 1, 0,
Yeah.
and alpha J2 is beta.
No. Okay. So now let's plug in the values. I'm calling this. Let's give it the name my root vector number 1.
Yeah.
Okay. Root vector minus 1. Okay. So this is root vector number 1, and my and the component, the first component, or root vector number 1, in that case will be 1 divided by the square root of 3. Okay.
Where did you get that from? Okay.
Yeah.
1 over square root of 3, where did you get that from?
You know, because those are the roots. You obtain the roots from the hexagon diagram.
So aren't these the roots? roots, the alpha, beta?
Yes,
alpha,
yes, and you normalize the root to have a given length, and then by trigonometry you are able to evaluate the components of these vectors.
So it doesn't matter which one is the first or which one is the
No.
second order.
Yeah,
Just- okay.
you just choose one.
So I was under the impression that that vector alpha is 1 comma 0, but that's not right.
No, no.
It's 1 over square root of 3 comma 0.
Yes.
Somehow the
Yeah,
normalization-
and then you have number, and then the second component is 0, because of course this guy, if you choose your axis like this, the second component of this vector is 0.
So you have assumed that you have computed the roots first.
Oh, yes.
And they have,
Of course.
So, and we haven't gone over that.
Yes,
Okay,
yes,
fine.
yes, yeah, okay. And then you go ahead with the second root. Okay, let's suppose, okay, that the 2 and the minus 2 correspond to this beta here. Now beta will have a component along the x-axis and the y-axis. So when you look at the components, you see you have a negative 1/2, because you see this root vector points west, right? Northwest.
That's the confusion, right? Because when I was reading this root spaces thing,
Yeah.
sometimes some authors define the vectors in the alpha beta space,
Yeah,
and sometimes in the Euclidean space.
yeah, you're
So in the
right.
alpha beta space, the vector alpha is 1 comma 0,
Yes,
and in the Euclidean space, it is 1 over square root of 3 comma 0. But here we
Yeah.
take the Euclidean space,
yes.
not the alpha beta space
Yes.
vector.
No, yeah. Okay, so you look at the beta vector, you see it points northwest. Okay, so if you look in the x direction, we'll have a negative coordinate, and in the north direction it has this. Remember, this angle here is 60 degrees. Okay, this angle is 120, and this angle over here is 60 degrees. That's where you get the 1/2 and the square root of 3 is divided by 2. And of course, this overall multiplicative factor is a normalization coefficient. Okay, so if you forget that for the time being about these prefactors of 1 over the square root of 3, you'll see this 1/2, the square root of 3 has to do with the cosine of 60 and sine of 60 degrees. You know, that's where it comes from. Okay, then you go to root vector number 3, which is the linear combination of beta plus alpha. Okay, you have this guy. And does it make sense? Okay, let's suppose I have a 1 here, and if I add minus 1/2, I will get 1/2. Right? 1 minus 1/2 is 1/2. Because, well, this all factors out. The 1 over the square root of 3 factors out. Now, if you have a 0 here, and if you add the square root of 3 divided by 2, you get the square root of 3 divided by 2. So these are the components. These are the components up to a normalization of my superpositions of alpha mass plus beta.
So here you're assuming that you're choosing the orthogonal basis, but I could be wrong. I thought you mentioned earlier that the choice of basis is an art, so I could write those alphas
Yes.
in any convenient basis.
You can write any inconvenient basis you want.
Commutation relation structure would still be the same, perhaps a little cleaner without the square root of 3.
Yes.
Is that
Yes.
okay?
So once again, I have one vector on the mirror conjugate. I have another vector on the mirror conjugate. I have another vector on the mirror conjugate. You know, and this way you get the 6 root vectors, whose tip vectors live on an hexagon. Okay, and of course you can rotate your axis at will, or you can rotate your hexagon at will. But you want to be clever enough to choose the right axis, you know, to simplify life. Okay, now let's look at the combination of E1 with -1. So essentially you're looking at the commutator of root vector alpha with the commutator of its opposite, the mirror image, and you're going to get H1. And the same thing when you look at the commutator of 2 with a -2, you get this. You know, and then remember, 1 minus 1 is going to give you, when you add them together, gives you 0, because 0 is an index associated with the Cartan subalgebra. You see 2 and minus 2, when you add them up, you get 0, and then you have to, the commutator has to give you a linear combination of your Cartan generators, okay? A 3 with a minus 3, again, is going to give you 0. 3 plus 3 is 0. So the commutation relation has to give you a linear combination of your Cartan generators, okay? Let's keep going on. Now, let's look at the other combinations. The other combinations, of course, this is where the n coefficients, remember earlier, those n coefficients? I told you, these n coefficients here. Look at all these values. Okay, it will be plus the square root of 6, well, plus 1 over the square root of 6, plus or minus the square root of 6. So now this is why when you plug in these values of these coefficients given by this is when you are going to get this square root of 6. Remember, 1 plus 2 gives you 3.
So you only need to calculate one of the n subscript coefficients,
yes,
and everything else will just...
Yes, because all of the others, you see, they have all this relationship between the coefficients when you permute indices. Yes. Then 2 with a minus 3, well, 2 plus minus 3 gives you a minus 1. But this is the minus 3 with a plus 1 gives you a minus 2. So that you get all these other combinations, okay? And these are the commutation relations of your generators associated with your root vectors of your SU3 Lie algebra, written in the Cartan basis. Yeah, something crossed your mind, Dugan. I'm sorry?
This is the same that if you multiply the Gell-Mann matrices.
Yes, this is okay. Now, this is kind of abstract. As a physicist, we like to play with matrices. So what do? Well, we want to look for in interpretation of these vectors. Interpretation of the generators associated to these vectors. Because when I speak of vectors, I mean generators associated to these vectors. Okay. Now I want to find a one-to-one correspondence between those generators in terms of the Gell-Mann SU3 matrices, okay? So the diagonal matrices will correspond to your Cartan generators because the diagonal matrices commute with each other. So that will be the natural choice, right? And then the other combination, the other 3 pairs will be given by these linear combinations of the plus minus. And here, again, I'm introducing the i's, okay? Those i's are very important, okay? Remember, the Gell-Mann generators, when you look at them, they're all Hermitian matrices. So when you take your, then I'm going to define these generators by superposition. So remember, this is a Hermitian generator. Lambda is Hermitian, but when you multiply by I, you get an anti-Hermitian object. Okay, so these matrices will have a Hermitian part and an anti-Hermitian part. Remember, when you have a matrix, any matrix can be decomposed and antisymmetric. Well, the same with here. A Hermitian matrix, any matrix can be decomposed into a Hermitian piece plus anti-Hermitian piece. So you do this pairing. The 1 with 2 gives you this, the 4 with the 5, the 6 with the 7, and the only remaining ones will be attached to your Cartan basis generators, okay? So remember, these are the Gell-Mann matrices that I gave you. They are all traceless, they are all Hermitian. And remember, this is your diagonal matrix. And the next one, the lambda 8. And remember, this is a normalization factor because all the matrices are normalized such that when you square the matrices and you take the trace, you get 2. Remember, when you look at the Cartan matrices of your algebra, remember that along the diagonals you have 2's, 2's, 2's? Yes. Okay. Of the diagonal, you're going to have zeros, minus 1, minus 2, minus 3. But then when you look at the diagonal, you have 2's. Okay, so the physical interpretation is that you normalize all these matrices in such a way that when you take the square and then the trace, you get the 2. Okay? So when you square this matrix and you take the trace, you're going to get 2. Do you agree? Dagan, you don't believe me. 1 plus 1 is 2. plus minus 2 square is 4. 4 plus 2 is 6. You have the square root of 3. A square is 3. 6 divided by 3, you get 2. Okay? And the same happens with all these other matrices. Okay? Because Dogan did not believe me.
I think now he disbelieves you.
Yeah. Okay, so now let's use the correspondence of the Gelman matrices. So I have my matrices. So I have a one-to-one correspondence between the generators in your Cartan basis and the Gelman matrices. So now I can just evaluate the commutators by evaluating the commutators of matrices. Okay? And when you do that, remember, you will get the same answer up to factors of 1/3 because it was a normalization factor. So when you do the commutation relationship of all these matrices, you know, you will be able to deduce these eigenvalues, which are the same, exactly the same I had before, up to a normalization factor. Okay?
The basis that I choose doesn't have to be orthonormal, right?
No.
Any basis will work.
Any basis, yeah, any basis. Well, in reality, when you have two matrices, when you commute them, you have to have a linear combination of the other matrices, right? If you have an algebra, when you commute two matrices, the only thing you can get is a linear combination of the other matrices, right? Well, of all the other matrices, because a matrix space, I mean, it's a linear space. So essentially, okay. Now the Weyl reflection. Okay, the Weyl reflection is something very important because here, of course, I gave you the trivial Weyl reflection with respect to the origin, you know. By Weyl reflection, you means when you have two roots. Let me get the eraser. Yeah. Suppose I have one root alpha, which I call alpha, and another beta, okay? So before you do anything, what you usually do is that you have your two roots, which are vectors. So you draw, in general, a hyperplane perpendicular to each one of your roots, okay? So in this case, let's draw a hyperplane perpendicular to my root alpha, okay? So now I want to reflect root beta with respect to this hyperplane that is perpendicular to my alpha root, okay? So this is what I mean by this operation. The reflection of the root beta with respect to an orthogonal hyperplane to the root alpha is given by this formula.
So that's how the roots are defined.
Well, you start with the simple roots and then you perform reflections. Yeah. So, I mean, as an exercise, I mean, I think it's very nice. You could do it. I mean, it's not very hard to prove. It's just doing vector or algebra. It's not very difficult. I mean, I can prove it to you, but I mean, it's not that hard. So what happens? The Weyl reflection will give you this vector. Beta prime. This is what this means. Now, what happens if you replace, in this very special case, if you replace beta with alpha? Okay, if beta becomes alpha, you get alpha minus 2 alpha, you get, okay? Because it makes sense. The reflection of alpha with respect to the mirror will give me negative alpha, okay? So this is what I mean by the Weyl reflection of a root with respect to another, okay? So the Weyl group, okay, so this group is so the totality of reflections that you can make in your root space is what you call the Weyl group associated to that given Lie algebra.
So the Weyl group is a set of transformations,
yes.
The reflections in this case?
Yes.
So the beta prime should be the one on the lower left, right? Because it's a beta reflected over
No, it's reflected over a plane perpendicular to alpha. Look at the mirror, okay? Okay, so let's look at the other plane which is perpendicular to beta. Okay, this is the plane perpendicular to beta. Okay, and this is the plane perpendicular to alpha. Okay, so you see this domain here, this region comprised of the overlap of the intersection of those two planes. That region is what people call the Weyl chamber. Have you heard?
Yeah,
Yeah, okay. This is the Weyl chamber. Yeah, the Weyl chamber. Yeah, the torture chamber. Okay.
And why is that?
It's
to part of a lay.
Yeah.
What is a suppositor was mentioning about the chamber, like from the chamber.
Yeah.
You can also like a mirror chamber, like you.
Yeah.
Why is it torture?
Oh, I call it torture chamber. That's a joke. It's a joke. It's a joke. Yeah, yeah. So okay, so it's like a fundamental domain, you know.
Yeah.
Okay, so what the Weyl group will do in general is will map when you have an hexagon, right? Remember that the root space of SU2 led to an hexagon. You have your vertices. You have 6 vertices, so you're going to have 6 regions, of your hexagon. So each slice of the pie of the hexagon is like the Weyl chamber, and of course, under reflections, you will map one chamber into another. Okay.
Isn't it the same than the Coxeter group?
It's related. Yeah, it's related to the Coxeter group. Yes. Okay, so the hyperplane is perpendicular to the simple roots. Okay, remember the simple roots. Because remember, the simple roots are the building blocks that allow you to generate the other roots. I'm talking about the Weyl chamber associated to the simple roots. Partition your root space into finitely many regions called the Weyl chamber. Okay? Yeah. Now let's look at the classification of Lie algebras. When you look at your books, the actual classification really is made for complex Lie algebras. We'll talk later about the real Lie algebras, for now we're going to draw pictures in a real Euclidean space. But keep in mind that in reality this classification was made for complex Lie algebras. Okay, so the A root space, the A algebra, the A series, okay, this is the A, B, C, D, and the E, the exceptional series. The A series is, many authors, when they see A sub n, they say it's the algebra of SU n plus 1. And this is the special linear algebra, n plus 1, because remember, in this particular case, n is the rank, and it's associated with the SL n plus 1. When you have rank 1, you have SL2. Okay, remember the SU2 algebra it lives really inside the complex SL n algebra. Okay, but to be rigorous, mathematicians define it like this. The B algebra is associated with the odd orthogonal algebras. The Cn is associated with the symplectic algebra. The Dn is associated with the even orthogonal algebras. And the exceptional algebras of ranks 2, 4, 6, 7, and 8 are based on the exceptional groups. Okay, the G2, F4, E6, E7, E8. Okay, so SUN is in here. It's in here. Okay, so remember the SUN algebra is really, regularly speaking, a real algebra, despite the fact that it's made out of complex special unitary matrices. It's really a real Lie algebra that lives inside the complex SLN algebra. Okay? Yeah. Okay. Okay. Now the real dimensions of simple Lie algebras. Remember, I I brought your attention to those pages at the beginning. And remember, if you look at your book on page, let me see if I have the right pages. Okay, from pages 310 to 313, you have the root diagrams. And then if you look at page 292, you will see a table, okay, in page 292, you know, with the roots, the number of non-zero roots, the total dimension, etc., etc. It's in your little book. Yeah. You have it? Yeah, okay. So the AAN algebra is associated with the SL n plus 1. So the number of generators, the special linear group in n plus 1 dimension has this, the number of generators is given by this formula. Okay. In the case of the odd orthogonal group is given by you know, the number of antisymmetric pairings you can make. The same thing with the symplectic, and this is the dimension of the even orthogonal group. And of course, here the book also, and here tells you how to construct the simple roots written in terms of a Euclidean basis. Okay, so you take a Euclidean basis of vector and you perform these combinations of plus and minus. You can generate the simple roots. Okay, of your algebra. Okay, for example, for the exceptional algebras, for the G2. Remember, the G2 has 14 generators. It's rank 2. That means that you only have 2 simple roots. And you can make these combinations of pluses and minuses, and you can generate all the roots, the 12 roots, including, and then the same thing with F4 and E6, you know, and then also with E8. You know, I think this is how you construct the root lattice of E8, if I remember, where you could have this could be positive numbers or 1/2. Raymond, remember that? Yeah. You can take an even number of plus signs. So this is all in your book. You know, all the details of how you can generate the simple roots. And then all the other roots, and when you look at all the combinations that you can make, this is how you can generate 248 of them. Okay, for the E8. Now the Dynkin diagrams. Are you familiar with the Dynkin diagrams? Fang, you're familiar?
Yeah.
And you guys, Aaron, Russ, a little bit. Yeah.
Yeah. We learned about it in Prague.
Okay. So if you look at the pages that I have, yes, you can look at the book and you can look at the screen at the same time. This will help you. If you look at the book and if you look at the screen, okay, so what you do is, okay, before that, remember, any root vector is a linear combination of your simple root vectors. Okay, capital V is a root vector. It's a linear combination of your simple roots. Okay, your simple roots are like the building blocks. You know, how you by performing linear combinations of your simple roots, you generate the other roots V. Okay.
On this diagram on the board, you had beta and alpha.
Yeah.
Now it's like alpha 1 and alpha 2.
Yes. Yes. Correct. And okay, so a root is positive, you know, if the numerical coefficients involved in the superposition are always positive, you know. And what they call the level of the root, you know, is given by adding the entries, you know, the coefficients attached to each simple root. Of course, a root will have higher level you know, the higher this summation will be, you know. For example, the first simple root is 1, that the first coefficient is 1. And alpha, let's suppose here for V I have alpha 1. So alpha 1 equals to alpha 1. Trivial, right? So the first coefficient is 1, right? Alpha 2, in this case, will be alpha 2 is equal to alpha 2. So that it means that the first coefficient will be 0 and the second coefficient will be 1. Okay? And all the other roots will involve linear combinations of the simple roots. And then, of course, the level of the root is given by summing all these numerical coefficients. Okay? So by a highest, a root will have a highest level, will be the root whose numerical coefficients are higher and higher and higher. Okay? If you have root 1 trillion, obviously it will involve a linear combination where these coefficients will have a very high weight. Okay? Now the n simple roots will determine a hyperplane, an n-1 dimensional hyperplane passing through the tips, you know. Because, for example, we know that a two-sphere can be represented by an analytical equation given by x squared plus y squared plus z squared. So a two-sphere will require 3 numbers, 3 coordinates to define it. You know, in the same way, n simple roots correspond when you draw the root diagram in any dimensions. When you look at the tips of those vectors, all those roots, n of them will determine an n-1 dimensional hyperplane passing through the tips. You know, this, you know, what I'm talking about deals with the geometrical configuration of the tips of your root vectors. It's not so important. The thing you need to know is that the tips of those vectors live in hyperplanes. And you'll have a family of hyperplanes. Okay? So each hyperplane will give you a level number. Like I live in floor number 1, I live in floor number 2, I live in floor number 3, I live on floor number 100, okay? So those floor numbers, those hyperplanes, the level, the height of the floor you live in is associated with these numbers here. Okay, you know, the higher these integers are, the higher the floor you live in, you know. Okay, and then the root spaces can be divided into 3 disjoint parts. Okay, the 0 roots corresponds to the Cartan algebra, and then you'll have a plus and minus. You know, remember when you have a matrix, it can be broken into a diagonal matrix, an upper triangular matrix, and a lower triangular matrix. So here is the same idea. You have a space, and you can break it into a plus, 0, and minus. It's like having the upper triangular matrix, the diagonal matrix, which is associated to the Cartan subalgebra generators, and the lower triangular matrix. Okay, so you can break your root space, your root vectors. Imagine there are matrices, you can decompose them into upper triangular, lower triangular, and diagonal. Okay, so this is the correspondence. This is your root space, and corresponding to your root space, you have a bunch of matrices. Okay, so this is upper triangular, lower triangular, and the diagonal. So I'm going to ask Ray, name these triangles. Yeah. George, Eugene. Okay. Okay, so this is the plus triangle, means it's the upper triangular matrix.
That will be in the interrogation.
Yeah, yeah. This is the lower triangular matrix, and this is the diagonal. Okay. Okay, what is a simple positive root? A simple positive root is a positive root that cannot be written as the sum of the other positive root. Okay, so remember, if alpha and beta are simple and positive roots, their sum is a root. But remember, alpha and beta now are the simple roots. Okay, it happens that if alpha and beta are simple, the summation is a root, but their difference is not. But these are simple roots, okay? Don't confuse the simple roots with the other roots, okay? So if alpha and beta are simple positive root, then the inner product is less or equal to 0. And why? Because it has to do with the cosine of the angles. The cosine of the angles are associated with 120 degrees, and then you have 135 degrees and 150 degrees, and then 180 degrees. Okay, it's all in your book. Okay, I'll go into this into a minute. Yeah.
Simple negative root? Can you give one?
A simple negative root, in my case, will be here. This is the simple positive root. So minus alpha will be a simple negative root.
So the negation of all simple positive roots and simple negative roots?
Yes. Okay, so when I take the scalar product of the unit vectors, you will see that Cartan was able to prove that you only have these values. Okay, and remember, when you take the scalar product of two vectors, you take the norm of one vector times the norm of the second vector times the cosine of the angle in between. So the inner product really specifies the length of your vectors and the angles. Okay. So now when you look at your page, 310, 312, 313, in order to draw a Dynkin diagram, you can look at your book. Yes, it's too bad that I lost that page that I gave Fang yesterday. Yeah, it must be somewhere. Ah, wonderful. You could pass it around. You also have it in your book. Okay, good. So good, thank you. So what happened is that you represent each simple positive root alpha I by a dot. And as Fang was saying, the number of simple positive roots coincide with the rank of the algebra. Yes. Okay? I'm talking about the number of simple positive roots. So you represented by a dot. Okay, so you connect the dots for each pair of roots by n lines. Okay, so dots which are not connected by lines represent orthogonal roots. Some people place the relative value of the length of the roots above by a dot. Although it's not necessary to do that. Since the angle between vectors determine the relative lengths, it is only necessary to specify which root is bigger by an arrow. Okay, like in the Dynkin diagrams of G2, B2, and C2. If you look at the Dynkin diagrams of G2, you only have two simple roots, and you're going to see three lines, two dots with three lines and an arrow. So the arrow points in the direction of the smaller root towards the bigger root. The arrow points an increase in order, an increase in size. So it points from the smaller root to the larger root. Okay? So the total number of lines connected to any vertex is at most 3. Okay, so let's give you a specific example. When you see a single line, all the roots are of equal length, and their angle is 120 degrees. When you see a double line, it means that the ratio of the square of the length is 2 to 1. The ratio of the squares of the length is 2 to 1, and the angle is 135. For example, if I think B2 is that example. The triple line is when the ratio of the square of the length is 3 to 1. The angle is 150 degrees. In that case, is the simple roots of G2, for example. Okay. Okay. So look at well, I guess the picture you. Oh, I'm sorry. That paper essentially. You have all the drawings in your book in pages 310, 311, 312. Okay.
Question?
Yes. Let me see that. Yeah.
Between B2 and C2.
Yeah.
They look the same, just they are symmetric.
Yeah.
So it depends of what is alpha 1, alpha 2.
Yes.
But what is the criteria to determine which one is alpha 1?
Yes. Well, at the direction of the arrow, it will tell you which is bigger and which is smaller.
Yes, but
Yeah.
if I exchange alpha 1 and alpha 2,
Yeah, but
You can't change it because the relationship are different.
yeah, then you will have to flip the sign of the arrow, right?
The last one does not have a direct connection.
Yeah, because remember, if the roots have different size, different length, then you know which is one and which is the other, right? Yeah, yeah,
You see the first one
yeah,
has this straight connection of 3
yeah.
to the previous one, but the last one does not have that threefold connection.
Yeah, and then they also write. You see these numbers that right above, 2, 1. It has to do with the relative length of your roots.
Oh, is that the ratio?
Yes, the ratio. Yes, the ratio of the length square.
yes, for B2
Okay.
and C2.
Yes, the ratio of the length square. Because remember, the length you have to take the square root. Yeah, yeah. Okay. Yeah.
When you have two vectors,
Yes. Yeah.
do you say that this one is U1 and the other one is U2
Wha-
and not the reverse? For example, that alpha
Ah,
is alpha.
Well, in other words, why do I call alpha alpha and beta beta?
Yeah.
Yeah, you're right. You're right. You have to choose. It's up to your choice. Yeah, yeah. You have to choose one or the other. You're right. Yeah, yeah.
It's kind of like the ones in the middle that you can.
Yes. I mean, you're right. I could have defined my axis in a different way. I could have rotated my axis and called beta alpha and alpha beta. You're right. You're right. Remember that these algebras also have automorphisms, and automorphisms have to do when you exchange the roots. That's right. These algebras have automorphisms, and you can exchange roots. You're right. You can flip one root for the other. And if the algebra remains the same, that means you have an automorphism of your algebra. Yeah, yeah, yeah.
So
Yeah.
how,
Okay, okay.
are
Yeah.
you sure
Yeah.
the arrow is pointing from the small one to the big one?
That's a convention that people use. Yeah.
Seems a bit conflicting.
Yes, yes. Yes. Yeah. I will show what Ray, let me see, because I don't have my glasses with me. Let me see if I go at the chapter on real forms at the very beginning. Okay, real forms, let me see if I find it. They give you all the automorphisms of your Dynkin diagrams, means you can exchange the names you attach to your roots. Okay?
The immediate ones.
Yes, and then no, because this has to do with the automorphisms of your Lie algebra. Let me see. Yeah, actually, this is a long chapter. Yeah. Okay. Look at page 324. 324. (324) gives you the automorphisms that you have of a given Dynkin diagram under by exchanging the roots.
Yeah, that's what I'm saying because
Yeah.
this book for B,
Yeah.
the arrow is pointing to the right, but
Yeah.
this book is pointing to the left.
Yeah. Yes.
So
Yeah.
they're like off.
Yes, yes. Okay, do you see page 324, Raymond?
2, 4,
Yes. You see how they exchange the roots among themselves when you have a symmetry of your Dynkin diagram? Yeah, yeah.
Yes.
Yes, yes.
So does that mean that E8 doesn't have an auto?
E8 has a trivial automorphism, yeah. But notice the D4. D4 is, for example, SO8 has this triality property. Remember that when you have a spinors vectors in 8 dimensions, you have this triality. Yes, D4 has a triality, G2 doesn't, but E6 has. You see, and E7 doesn't, okay? But if you look at C, because oh, my glasses, look at, yeah. B, and notice in page 324, if you look at the diagram Ray between B and C, notice that there's a difference between the two of them. because one arrow points to the left and the other points to the right. You see? You see, Raymond, in the
Yes,
yeah. So they are different. They are different, yeah. Okay, yeah. Okay, so can I proceed, Dugan? Can I proceed?
Yeah.
Okay.
And
Okay.
why do we have only one G2 and not two?
G2 has rank 2, so you only have two simple roots. So you only have two dots.
Yes, but compared to B2 and C2.
Yeah. Well, no, but in that case you must have BN, CN. Yes.
G does not have GN, right?
Huh?
G only has G2.
G2 only has two roots. Yes. BN has many, right?
Whereas the arrow in the other.
Okay. When you take B2, okay, let's look at B2 and C2. Then what you have to do, you have to remove all the nodes and only keep two of them.
Yes.
Yeah. So you will.
So since there are only two, so the error does not really matter. It's one or the other. But in the B and C case, there has to be an error because
Yeah.
it matters because the connection to other roots.
But
Yeah.
not for two, B2 and C2.
Yes. So in that case.
But they're drawing
Yeah.
BN.
Yeah.
Oh,
Yeah.
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 Yeah,
Yes.
maybe B2 and C2 are equivalent.
So then they're isomorphic. In that case, there will be isomorphic algebras.
Ah, oh, that was
Yeah,
my
B2 and
question.
C2 are the same.
They are isomorphic in that case. Yeah.
That's what happens when you switch the roots.
No, I answer.
That will be an automatic. Yeah.
Understanding why there was two diagrams.
Yeah.
So the only answer is that they are isomorphic.
Yes. Yes. Does that make sense?
Yes, it makes
I
sense.
hope.
Otherwise, it doesn't make sense to have only
Yeah.
one G2.
Yes. Yeah. Okay. Now, okay, let's look at the Coxeter number. So there are many ways to define the Coxeter number associated with a root system. So a Coxeter element, as Raymond was mentioned, is the product of all simple reflections. And the product depends on the order in which they are taken. So, for example, the Coxeter number is defined by taking the number of roots divided by the rank. For example, the Coxeter number H, that's how you label it, associated with E8 is given by 240 roots. Of course, you don't include the Cartans of algebra, you include the 240, divided by the rank, which is 8, and you get 30. Okay? For example, the Coxeter number of G2 will be, the number of roots will be 12, divided by the rank, which is 2, so 12 divided by 2 will be 6, right? And so forth, okay? So, another way of defining the Coxeter number is related to the highest root. Remember, I mentioned that a given root can be written as a linear combination of your simple roots. So if you take the highest root, meaning that the values of m are the largest, so the Coxeter number is also equal to this relationship. 1 plus the sum of your coefficient. Okay. You have the book that I suggested, the ADEX book. Okay, so you guys will be reading that book. Yeah? So it's a small book, but it's all related to the Coxeter graphs and why they're so important, and all the interconnections they have with physics. Okay.
Another question about this.
Yeah.
Is that as Coxeter group we have also H3 and H4 and also H2?
You mean are you talking about the non-crystallographic book
Yes,
groups, the H2,
So
H3?
they have irreducible root system.
Yeah.
But they are not the algebra.
Ah, yes. So, but you must have a definition
They
of.
are root system of what?
Yeah.
In this case?
Yes. So they are, but what he means they are non-crystallographic, but they must be associated to some algebra, right? I have to look at the paper by Deschamps.
He does Clifford algebra, right?
I have to look at the Duchamp paper, and I'm sure
It's a Coxeter group.
it must have to. It must, but it's associated with the Weyl reflections.
Yes.
It has to be associated with the Weyl
It
reflection.
has a Dynkin diagram, but there is no Lie algebra or Lie group.
Yeah, yeah.
H.
Well, the Weyl group is a discrete group. It's like the group of automorphisms of a given algebra. It's a discrete group. It can be associated to a Lie algebra, or it might not necessarily be associated to a Lie algebra.
Ah, yes.
Okay? It's just a discrete group.
So this is
Yeah.
an exceptional case when it is not associated.
Yeah. And this is what you mean non-crystallographic? What do you mean?
Oh, I don't know what he means by non-crystallographic. I just thought
Yeah.
he means that it is not any one of those ones that is listed ADEA.
Ah, okay. I see. I see.
Maybe means non-periodic.
It shows that there is no lattice.
Yeah. Ah, you're no lattice. Yeah. Yeah. Okay. Okay. Yeah. Okay, I'll briefly mention a little bit about representations of finite dimensional Lie algebras. Remember, you have this book here by Fulton and Harris, on representation theory. You have it. Who is the one who got it?
What?
Is it yours?
Not the Fulton and Harris one, no, the Penrose one is.
Ah, okay, Fulton and Harris. You have this Springler-Bergla, graduate text in mathematics, all devoted to representation theory, which is a very fundamental branch of mathematics, But, we're not going to do... Okay, representations are important when you want to classify the particles, when you want to build a unified field theory. And then you need to know a lot about representations of groups. Okay, so I promised I was going to bring you the link to this paper in the archives, 1,851 pages with 836 tables. It's called Finite Dimensional Lie Algebras and the Representations for Unified Model Building, So maybe David can read because I cannot read very well. My glasses, I have them, we give information since David... yeah.
You want me to read?
Yeah, you can read it.
What am I reading?
The abstract, yes. Yeah. And then I'll give you the number, of course.
We give information about finite dimensional Lie algebras and their representations for model building in 4 and 5 dimensions. Example, conjugacy classes, types of representations, wheel dimensional formulas, Dynkin indices, quadratic Casimir invariants, anomaly coefficients, projection matrices, and branching rules of Lie algebras and their subalgebras up to rank 15 and D16.
Yeah.
We show what kind of Lie algebras can be applied for grand unified theories in 4 and 5 dimensions.
In 4 and 5 dimensions. If you want to go to the higher dimensions, imagine, okay? So here you could pass it around and you can get the preprint number, okay?
What is the preprint?
Yeah. Ambrick will tell you. Yeah. For me, the most important really are the first 100 pages. The rest are essentially tables.
And it's 1100?
1,851 pages.
That's very, very short because Tony Smith has one on Vixtra about 40,000 pages.
Well, Tony has a web page.
It's one paper on Vixtra, it's all his website.
No, but he has, but no, what happened is that he has a web page that he has built for 30 or 40 years. So the field gives allow him to post his website in the Vixtra archives.
Yes.
Okay, so what he has is his website.
Yes.
That's what he has, yeah.
I believe it's a record.
Yes. So, I mean, I browse, you can pass it to Dogan. I browse through the paper. I remember the first 100 pages are, so they are, okay, and you can give it to the other. Essentially, is the question you were asking me, Ambrick. Okay, you have a bunch of groups. What can you do with them? How can you build models of particle physics? So you have thousands and thousands of unification models. Which one does nature choose is a big mystery. Okay, well, of course, all of them have to lead to SU3 cross SU2 U1, but you can embed SU3 cross SU2 cross U1 in many, many different ways. Okay?
But we want also gravity.
Huh?
We want also gravity.
Gravity, yeah, but gravity, I'll give you the reference about gravity. Gravity, as I pointed out, SO10 is a grand unified group, okay? SO10, okay? Okay, so for gravity, the only thing you need to do is take at least the Lorentz group, okay? And you take the direct product with SO10, and this group lives in SO 13,1. Okay, and I gave Amrik also in the paper. You know the Lebanese physicist that works with Alain Kohn, Ali Shamseddin. I always forget. Do you have two Ds or two N's? Two Ds. Okay. Okay.
Is this published or?
Yes. Oh, because I can never remember which way it is. He has another author, okay? Remember, Nesti, Percace, and Lisi also wrote a paper related to these groups. I mean, you listed in the reference.
Yeah.
Nesti, the Italian guy, okay? Now you can take the conformal group, okay? The conformal group, and can you guys see? Okay, with 10. This is a subset of SO 14,2. This is also a very important group. Okay.
So you posed the question that
Yes,
you have so many of these combinations of groups, which one does nature choose?
Yeah.
So rather than asking that question,
Yeah.
which is a difficult question to answer,
Yeah.
can we reduce the complexity of the question by asking which one of these models can be reproducible in a laboratory? And does that even make sense to?
Well, at the end of the day, you have to perform an experiment, obviously, because physics is an experimental science, after all.
Is the effort in building models based on group theory directed in such a way that it is reproducible in a lab, or everyone is just coming up with their own? Because SU5 was never reproducible.
No, because the proton decay has not been observed. What was the lifetime of the proton? What, 10 to the 33 years?
9 years or something, yeah.
Yeah, that's always bound. Of course, remember when you go to higher energies, you go to more complicated groups. So the higher energy you go, the more complex your group becomes. For example, if you have E8, you imagine you have unification at the Planck scale, then you break your E8 group to E7 at an intermediate scale. You break E7 to E6 at another intermediate scale. And then you go down the cascade, down your ladder. Of course, it happens at different scales, at different energy scales. And then eventually we reach the world we observe today, and we have the scales that the Large Hadron Collider operates with, which is of the order of 10 TeV, right? 10 TeV, right? Yeah. So of course, as you move along the zoo of groups, you have higher and higher energy scales. So yeah, it's an art. It's really an art, you know.
But is the effort by the community, or is there any effort in the community to eliminate some of the things which are not reproducible, or if there is not, then why not?
Well, they are working with extensions of the standard model. The standard model seems to work very well. The SU3, SU2, U1, now that the Higgs has been found. Now what people are doing are extension of the standard model. They are trying to see if there is an observation that does not fit the standard model, and they try to see what group that particle will represent, you know. They found this strange event in Switzerland, this 750 G, the diphoton, and then of course when people found that effect in CERN, the following day you had 1,000 papers, everybody had an explanation for it. starting from F theory, string theory, all the way to esoteric physics. So, and every day you have a website devoted to the 750 GeV diphoton effect. Yes. So you have to be lucky. In physics, you have to be lucky. Like Einstein was very, very lucky that Eddington was able to observe the deflection of the photons, when they went around the sun. I think he went to Brazil to observe that effect, right?
The photon.
No, the photon, when the sun deflected the photon.
Yes.
I think it was in Brazil. I think there was an eclipse of the sun, and you can see how the light of the stars behind the sun bend. And I think it was done in Brazil. And Eddington was able to do it, and Einstein became a household name after that. So he was very lucky. It took 100 years to detect gravitational waves. So it took 50 years to find the Higgs boson. It might take, who knows, might take 100 years to see if string theory makes any sense or not. Yeah.
How does the gravitational waves phenomena manifest in your extended relativity model? Or have you thought about it?
No, I haven't thought about it, But I mean, when you have a linear perturbation of the theory, the gravitational wave is just a linearization of your non-linear theory. So you always have wave-like solutions to any theory, really. When you linearize them.
So is your model also a linearized version?
You can linearize the theory. You can always linearize a non-linear theory. When you have very small perturbations around flat space solution.
That's what Kleiner did, right?
Kleiner wrote two interesting books. One on finite path integrals, which is more than 1,000 pages. A beautiful book about all the applications of path integrals in quantum field theory and physics. But then he's done a lot of work with dislocation and disclinations in crystals.
Which are like linear perturbations.
To find an explanation of torsion,
And
curvature. Yes.
Is that accepted in the community, the procedure to transform the Euclidean space into the Minkowski space through that linear perturbation? Is that
You could have curvature in Euclidean space. The Earth, for example, looks, when you look at the globe, it's like a Gaussian surface, so it's Euclidean, right? The problem I always say is the temporal dimension, because you could have a crystal embedded in a hyperbolic space. Yeah, I guess so. Yes.
What's
Yeah.
the SO3, 1?
Okay. This is the Lorentz group, where you have three spatial dimensions and one temporal dimension. Yes.
And this is also the Poincare group, right?
The Poincare group, you need to take the semi-direct product with the translation group.
So SO3 cross 1.
It's just the Lorentz. It's just the Lorentz group.
So SO3 cross 1 times something?
The Poincare group will be the semi-direct product, of course, of the Lorentz group. Okay.
You mentioned that in the slide.
Yes, and you have to take the semi-direct product that are write like this. Some people like to write it like this, with this symbol. Semi-direct. They like to be more artistic. And then, of course, the translation group. The translation group. In this case, in 4 dimensions. Actually, in 3,1. Yeah.
And what was? Can you remind again? Since we're talking about it, what is the semi-direct?
Semi-direct product. You have a semi-direct product because the generators of the translations do not commute with the generators of rotation. Okay, so because they don't commute, this is what you call them semi-direct. If they were to commute, then you call them direct. But because they don't commute, you call them semi-direct.
So is there an equivalent notion for the algebra?
For the algebra, yeah, these are the generators. These are the generators of my algebra. And from the group perspective, well, in that case, you can say that the SO3, 1 algebra, and then you'll have the semi-direct sum.
Okay, so
Yeah.
it's the same thing.
Yeah. Okay. Can I proceed? Yeah. Okay. So let me have the. You guys wrote down the paper and the reference. Yeah. Because then I'll forget. Yeah. Thank you. Hashimoto. No, it's not. It's not Hashimoto. It's Yamatsu. I was thinking of Hashimoto. Why was I thinking it's Yamatsu? Anyway. Okay. So essentially, representation. What you do essentially, you associate, for example, to a given generator, you associate a matrix in general, in such a way that the representation associated with the commutator is given by the commutator of your representations. So, if I yeah, so what it means, if I have the commutator of two generators, okay, so the representation associated with my commutator is given by the commutator of those matrices.
Okay, so
Yeah.
gamma?
Gamma capital is a representation associated to a generator X. Okay.
So for example, it could be a matrix.
A matrix, yes, yes.
So you're saying the matrix comprising of the commutator elements.
Yes.
So
Yeah.
the
Yes.
elements of the matrix are commutators.
Yes, yes.
Is equal to the commutator of the matrices.
Yes. So what I'm saying, in a more Christian language, what I'm saying is that the composition of two generators, when I take the representation of the composition, okay, this is the group composition, is given by the product of the matrices. Okay?
Is it the group product or any product?
No, this is the group product. Group product lives here. Well, the algebra. Well, in that case, if I have a matrix representing the algebra, the algebraic product, yeah, the product associated with the composition of my algebra.
But that is not the same product.
No, here is a matrix product.
That is a matrix product.
Yes. Yeah. So from this relationship, you can deduce this. Okay. Oh, sure.
Okay, carry on.
Okay, thank you.
Okay, so
Yes.
representation of finite dimension semi-algebra as the above discussion, we analyze the representation. So I'm trying to understand, when is this true again? Or is it always true for any Lie algebra?
For any Lie algebra and for any representation that people use the word faithful representation. It's another word that people use. You want the representation to be faithful, meaning is that you don't want you don't want to have like the zero matrix, for example. You know. Okay, so the identity element, you will choose. How will you represent the identity element? Is by choosing a diagonal matrix, right? That would be the natural thing to do, right, Raymond? To represent the identity element of your algebra, you'll assign the diagonal matrix. Yes, that would be the most natural. Now, what is the dimension? What are the size of these matrices? Okay, the sizes of these matrices depends on the dimension of your representation. You could have an infinite number of representations associated to a given algebra, to a given generator, because the matrices you can make them larger and larger and larger. So this is why it's really an art to find representations of an algebra.
But what is the interest to have big representation by matrix of bigger size?
Yeah.
If in fact you are representing the same than with small matrix.
Yeah, but let's suppose that you have a trillion particles instead of 20 particles. Then if you have a trillion particles, then you probably need a bigger matrix to represent all of them, right? For example, when you take SU3, you have 3 quarks, right? So the natural thing would be to represent the SU3 matrices by 3 by 3 matrices. You know, That would be the natural thing. And then when you perform an SU3 transformation, imagine you have a quark that has red color, a quark that has blue color, and a quark that has red, blue, green. Then you perform a rotation, an SU3 rotation. The natural thing will be to play with a 3x3 matrix, right? Yeah.
3x3.
Yes. If you have 8 gluons, the natural thing will be to use the adjoint representation, because the adjoint representation will be 8-dimensional. So you will have 8x8 matrices that act on your space of 8 gluons. Right? Yeah. That will be the natural thing. Yeah. If you have, and this is how, usually the adjoint representation is assigned to the gauge bosons, you know, for example. And the fundamental representation is assigned to your matter representations, to your fermions, you know. So it all depends.
Adjoint representation for which one?
For your gauge bosons, yeah.
And fundamental?
Usually for matter representations. But also, you could also assign an adjoint representations for matter as well. There are many unified models where they also assign an adjoint representation to the matter particles. But in general, what you do is the fundamental is usually assigned to your matter, and the adjoint to your gauge bosons. This is usually how it's done.
Is there really, is just that turns out to be convenient?
No, I mean, some people explain it to me. It's just the way, because the gauge bosons, I mean, when you gauge in algebra, the carriers of your force are carried by your gauge bosons, you know, and the way you define you have your gauge field, and then you have something which you call the field strength associated with an algebra. For example, in electromagnetism, remember you have your photon field, which is represented by your A mu. For example, in reality is like your vector potential. You have the temporal component, and then you have the other spatial component. Okay, this is your photon field, which corresponds to a vector field in 4 dimensions. Remember, the field strength, you know, the physical object you measure, because this object is not gauge invariant. The real object which is gauge invariant is the field strength, okay, which is given by this, and then you antisymmetrize, okay. So this object here will be like a matrix, like a tensor with 4x4 components, and when you write the 4x4 components, okay, because remember this object is antisymmetric, then you have to have zeros along the diagonal, okay, and here you write the components of your electric vector field, you know.
This is the electromagnetic?
Yes, electromagnetic tensor. And here, of course, it's antisymmetric. You have -1, -A2, -A3. And here, here you write the components of your B field. Okay? So in this way, you represent your electromagnetic field tensor. You define it in terms of your gauge field. You define it like this. And this is for the U1. Remember, U1 is in abelian algebra. It's trivial. Now, in the case of Young-Mills, you need to include the commutator. In case of Young-Mills, remember the algebra is non-abelian, so you have to include here. You have to include what you call the commutator of your Lie algebra. Here's your Lie algebra generators, bracket, the Lie bracket, okay. Okay, so this is a Lie algebra value field. It's a Lie algebra value because it carries a space-time index and it carries a Lie algebra index A. So in case of SU3, you have 8 generators because SU3 has 8 generators. These are your gluons. So you have to evaluate this commutator. And this is why you represent your gauge bosons. Your A fields are your gauge bosons, really. And this is why you assign the adjoint representation, because you are taking the commutator, you're taking this commutator of this generator with this generator. Okay? And this is how you get the structure constant. Remember, the commutator of TA with TB is going to give, and this is why you usually assign the adjoint representation to your gauge bosons. Yeah.
Are you gonna talk about the K representation today?
I'm sorry. Yeah.
K
No, I'm not going to talk about that because you probably know more than me. Briefly, the Weyl group, the Mackay correspondence. Okay, here I also made a note to myself because you probably know. The secret of the Mackay correspondence lies in page 312 and 313. It has to do with the automorphisms of your root space. So you're going to have this tetrahedral symmetry, octahedral, the cube, the icosahedral, and the dodecahedral. So in pages 312 and 313, well, actually starts earlier. You know, it gives you an explanation. I mean, this is in reality where you get the Mackay correspondence. You know, there is actually in the Wikipedia page, it has a very nice explanation of the Mackay correspondence. And I remember a few years ago also, you know, there has been so much written about the Mackay correspondence. But in your book, if you look at those pages, the key behind the Mackay correspondence has to do with the solutions of Diophantine equations, which appears in the classification of root spaces. And because you have those Diophantine equations, the solutions are related to the, you know, the Platonic solids and the discrete groups of the Platonic solids. In the book, you'll see why. Yeah.
Maybe in ADX book.
In the ADX book, of course, it's crucial. It's essential. Yes. Yeah. You know better than I. You know, because I remember when. No, because remember we had many emails. We had many emails exchanges a few years ago about the Mackay and the crystallographic groups. And the book by Coxeter. Coxeter has a book on real polytopes and complex polytopes. Yeah. Complex polytopes is something which I never had a chance to look at, but it's very, very tricky. But you have the ADX book by Sirag, and sure he must talk about it.
But that book, I have to say that it's not very easy.
No, why did he write why was he so stingy and write such a tiny little book? Except he could actually make it twice the size, right?
Probably more clear.
And more clear and with figures.
As an introduction.
Yeah, I think it's not written, it's written for experts.
Yeah.
It's not written for people who want to learn.
Because Klee wanted to read the paper here as a book club, and
Yeah.
I went through it. I was like, wow, this is going to be so difficult to read because
Yes.
even I couldn't make any sense.
Yes, I haven't had a chance to look at it. Maybe when I'm here, I could look at it.
Like his paper, the beginning was very easy,
Yeah.
and then
Suddenly,
it
just
Yeah.
I have no idea
Yeah.
what he's talking about.
Yeah, I don't know why they write this book for the experts. It doesn't
I
help.
think they all start writing with the objective that they can communicate with lower level people like me. But then soon they forget. They go in their tangents.
No, what he did in that book is he has a list of topics that, okay, ADX is related to all these topics in physics. So he got chapter 1, chapter 2. So I beg you?
So his paper is the same thing.
Really?
Well, his paper is much shorter, but at the beginning it's also super clear.
Yeah.
Do you think the AD is ADA or the ADs? Do you think that's an expansion of his paper?
Could be, you know. Did you meet him, Saul, in Oregon? Does he live in Oregon? Didn't he give you a copy of his book for free? He should have given you one.
So we bought them.
Yeah, because I wrote to Klee and I told him, look, I found this book that just came out, is about to come out in the market, so you guys probably will be interested. And you are the ones, the first buyers, were you?
Maybe, yes.
Yeah,
We
yeah.
got it before the date of publication.
Yeah, yeah,
Will Siraj come here if we invite or he doesn't
Yeah,
come?
I think he probably would.
yeah.
Yeah, he just
think
lived
that-
with his wife in a, area, and then that's not.
Maybe a better way to understand or read the book is to have him like Carlos and give us a 2-week lecture.
Yes, yes, yes. I could take a look at the book because I'm curious about it, and maybe if I come another time.
I can
So,
maybe borrow mine because I don't think I'll be able to read and comprehend that book.
you have a copy?
Well, it's Klee's copy,
Yeah.
so I can, if Klee's okay with it, I
Yeah,
can.
because Raymond has a copy, right? Or is it the same copy?
I think if
Everybody
you
has a
want,
copy.
you will buy your copy if you
4
want.
copies?
More than that, 6, 7.
Because everybody.
You know, those books are not cheap.
No.
Yeah.
They are not cheap at all, you know. Yeah. You know, when you go to the Library of Genesis, you can download everything you want.
And this one is too
Oh,
recent.
SciHub is not working nowadays.
No, because the U.S. government is boycotting it. My friends in Slovenia had problems to download the papers from SciHub, but there is a mirror site
What is it?
in Slovenia that is sciencehub.cc.
Science-hub.cc.
Yeah, I'll send you the link.
.bz is working.
Or .bz is also
Yes.
working? .io is not working.
No.
Ah.
.bz is working, but he's not making the research.
Yes,
He
yes.
put the GUI directly.
So,
When the viewer of this video goes to get coffee, during this conversation,
yeah. You are not recording, no?
I'm recording.
Oh, okay.
So it's useful. People will know about SciHub.
Yes, yes. So the lady, she's from Kazakhstan. Yeah.
and she's-
I hope the drones, she's not killed by a drone. You know? Yeah, okay. Okay, so we have enough for this week. Next week we'll continue. And then probably I should talk about the Deschamps. I have to prepare the Deschamps. I have to read it because he has 3 or 4 papers. But next week I'm going to talk about Clifford algebras, about Clifford 8 and E8 and E8 and Clifford algebras, and then I'll talk. I may talk a little bit. Yes, I think I have to give you a lecture on the basic on superalgebras. You cannot have a course on Lie algebras without knowing what a superalgebra is, because there is a very deep connection between the particles that we observe in nature and the 24-cell polytope. Yes, yes. So I'll talk a little bit about the polytope, the 24-cell, which you are familiar, and supersymmetry. Then I'll talk a little, of course, about Lie algebras and lattices, and a little bit about Kac-Moody algebras, hyperbolic, and then of course about the E8, the E9, the E10, and the E11. And then I'll talk about the Deschamps paper at the very end.